Hey there, everyone. We're moving into our next section, which is in Chapter 5. It's the only section that we're covering in that chapter, and it's on discrete random variables. And in many ways, this kind of wraps up our conversation on probability. It's kind of a cool section, one of my favorites, as a matter of fact, in the course. So let's dive right in. So objectives in this section are simple. We're going to work on calculating something called the expected value of a probability distribution. And the second thing we're going to look at is the law of large numbers. Now, before we can dive into this idea of the expected value, we got to define a probability distribution. Okay, now on our path to that, we first have to explain what a random variable is. So this section deals with something called discrete random variables. So remember, discrete deals with things like counts, right? Something very, very finite, very specific. The opposite end of that is something we call continuous. Now, we do look at some continuous variables in Chapter 6, something called the normal distribution. We say that's a continuous variable, and we'll understand that when we get there. So for now, a random variable is defined as a variable whose numeric value is determined by the outcome of a probability experiment. And the typical variable we use is x. And what we'll usually write is x with this little squiggly. And what we say is, let it be, the random variable x be, the rolling a six-sided die, for example. Okay? Or, let x be flipping a fair coin. Okay? So that's how we define this random variable x. And then within x, we get what we call outcomes, right? And so we have this little x, 1, 2, 3, 4, 5, and 6, right? And for flipping the fair coin, you can get heads or tails, for example. So the big X represents the random variable. That's the notation you're going to see. And the little x are the specific outcomes. Okay, so now we're ready to talk about a probability distribution, okay? So the first box here says that a probability distribution is a table or formula that gives the probabilities for every value in the random variable x. So what we need you to come out of this first definition remembering is that a probability distribution shows us two things. Number one, it shows us the outcomes. And the second thing it shows us are the probabilities. Okay, so very nice test question could be, what does a probability distribution show us? You will write, it shows us the outcomes and the probabilities of those outcomes. Very, very simple. Now the word distribution we've seen before, right? If you remember back in section 2.1, we had something called a frequency distribution. This is a probability distribution. So that word comes back to us yet again. Now you'll notice that we've got two very weird mathematical symbols that are written here, okay? And that's going to sort of help us in the second box here. So probability distributions, guys, they have rules, and there are two rules that make a probability distribution valid, okay? And you got to know these rules. Another good test question. What are the rules that make a probability distribution valid? Well, the first one says all of the probabilities have to be between 0 and 1 inclusive. What does inclusive mean? It means that we could have a probability listed that is 0. We could have a probability listed that is 1. Either way, they're locked between 0 and 1. And that's what this compound inequality is showing us here. Okay, that probability is locked between 0 and 1. Now, do you notice the big X here, that's the random variable, and the little x, lowercase, is the outcomes. And so that's the notation that we use, okay? And we'll understand that in the context of examples in a few minutes. So first rule is that the probability the probabilities in the distribution must be between 0 and 1 inclusive. The second rule is that the sum of all the probabilities has to be 1, okay? So remember, big sigma here, capital sigma means sum. So what this is literally saying is the sum of the probabilities equals 1, and that's how you write it mathematically, okay? Once again, you have to know both of these rules, okay? So what makes a probability distribution valid? Probabilities are between 0 and 1. Sum of the probabilities are 1. And what does a probability distribution show us? Outcomes and probabilities. Okay, very good test questions there. So here are 4 examples of probability distributions. Okay, let me move this down so we can still see those rules. So what you're going to notice is in the darker band here, this represents the outcomes. Okay, I'm going to draw my arrow a little bit better here. Those are the outcomes. There we go. And these are the respective probabilities. And what your job is to determine whether or not these are in fact valid probability distributions. And so what I would encourage you to do is to pause the video and see that they follow both rules that are listed above. Okay, let's see what we come up with. So go ahead and pause the video and give it a try. And so if they are valid, simply write it's valid, and if it's not, state which of the rules it's violating. Okay, so hopefully you've had an opportunity to try these, and so let's see. So the first one here, first thing to check is to make sure that all the probabilities are between 0 and 1, and they are. Okay, so that satisfies the first rule. But is the sum of the probabilities 1 for rule number 2? And the answer is no. Okay, and so this one violates rule number 2. Sum of the probabilities is not 1. So if you add up 1/2 plus a fourth plus a third, we do not get exactly 1. Now, if you look at the second one, we've got 1/5, 3/7, and 13/35. All of those are definitely between 0 and 1. So now what we have to verify is whether or not these actually sum to 1. And so I think if we convert to a CD here, 3 out of 35, and this one should be what, 15 out of 35. This, in fact, all sums to 1. So yes, this is valid probability distribution. Both rules 1 and 2 are satisfied. Okay. How about the second one here? Very subtle. Did you notice -3/8, right? All of these other probabilities are between 0 and 1, but -3/8 is not. Okay, so this is a no, as it violates rule number 1. And if you look at the last one here, 1/5 and 1/3 are okay, but 3/2 is not, right? 3/2 is 1.5. That's clearly more than 1. So this violates rule number 1, which says the probabilities have to be between 0 and 1. Something like this on a test, you got to be able to determine whether or not my probability distributions are indeed valid. Okay, so you either got to write the conditions or make a determination. And once again, notice probability distributions show us outcomes, which in this case are colors, and probabilities. Okay, now what we're going to practice doing is actually creating a probability distribution. So sometimes on the final exam, we're asked to do this. And what we want to do is to create one for X, which in this case is the sum of 2 rolled die. Okay, so you see that language here. So the random variable here is the sum of 2 rolled die. So what does that mean? It means we take a die, we roll it, we get a number, maybe 4, and we take another die and we roll it and we get maybe 1, and the goal is to add them. And what the sum that we get is the outcome. So what I've got here are 2 charts. The chart right here shows us the ordered pairs that we get. Okay, so this is sort of building our sample space. So what we're doing essentially is we are taking the ordered pairs, maybe this one, 1, 2, we add them up. 1 plus 2 gives us 3. So this distribution here are actually all of the sums. And if you remember in section 4.1, we actually created this very chart. Okay, and so if you had it in your notes, you can come back to it. And this is actually the chart that we need in this particular section. Okay, so again, all the numbers that are in black represent the outcomes, and so you could maybe call this die number 1, and you could maybe call the blue here die number 2. It's up to you. It doesn't matter the order in which you're labeling them. More importantly, what we're looking at here are what the outcomes are. Okay, so here's the chart. Here's the sample space that we're dealing with, and what I need to do then is to write out and create this probability distribution. Okay, so the first thing is we have to list the outcomes, and that's what's going to go in this dark bar horizontally here. So what do the sums range? Well, it looks like they go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so let's write them in here. There they are. And what we're going to write next are the respective probabilities. So the first thing you're going to notice is that there are, well, that's not showing up too well, that there are 36 outcomes. Okay, 36 outcomes. So what that means is that every one of my denominators here is going to be 36. Okay. Now, what the numerator is going to correspond to are the number of times that outcome occurs, okay? So you might want to pause the video, take a second and fill out the chart and see what you get, all right? And so hopefully you've got it filled in by now. So how many times does the sum of 2 come up? Well, I only see it here, so that's once. How many 3s are there? Looks like there are 2 of them. How many 4s are there? Looks like there are 3 of them. I'm getting stuff cluttered up here. There we go. And so in fact, there's a pretty cool pattern that exists. And I've done this so many times that I remember the pattern. And so the most sums that we have is actually 7. That comes up 6 over 36. Now, make sure you're paying attention to the online homework. Sometimes the online homework wants you to simplify the fractions. For our purposes, we're going to leave them here. And what I want to double check is that this is indeed valid. Okay, so remember 2 conditions to determine the validity of the probability distribution. First thing is all the probabilities are between 0 and 1. That is certainly true. I don't have any numerators that are bigger than the denominator, so I know that's okay. No negatives either. And the second condition is we have to make sure that the sum of all of these probabilities in this distribution is 1. And if you add them up, you'll get 36 over 36. So that's how I know my distribution is valid. So this is how you build one, for example. We're going to do another one in a few minutes. Okay, so there's the fancy distribution there written out nice and typed. Okay, if you maybe move the slides down, you could have cheated a little bit and saw what the answer was ahead of time. But it was a good exercise to build it. Now what we're going to do is some follow-up questions related to this distribution. So it's one thing to build it, but we also have to do some interpretation. So letter A here says find P of x equals 4. So the first thing we have to do is understand what the heck this is asking. So what this is really saying in plain old English is what is the probability that the sum is 4? That's what this is saying. Now how did I know that? Well, remember up here, if you'll permit me for just a moment, we said that x was the sum of 2 rolled die. Wasn't that how it was defined? That's how I know what x is. Equal sign is, and then 4 we know. So what's the probability we get a sum of 4? Well, that's nice and easy. It's right there. It's 3 over 36. Okay, and you can simplify it if you want. I'm going to leave it as it is. And remember, you can also express it as a decimal. Okay, I would suggest just leaving it as the fraction. Now take a look at letter B. This is the probability that x is less than or equal to 4. So this means we want the probability that the sum is less than or equal to 4. So when does that happen? Well, that happens when it's 4 or 3 or 2. So listen to what I just said. That means the probability that the sum is 4, the probability the sum is 3, and the probability the sum is 2. Notice the word I was saying? I was saying or. Do you remember back in probability? Or meant adding. Okay. So let's see what we get. Probability that x is equal to 4. We said that's 3 over 36 plus 2 over 36 and 1 over 36. So that's going to be 6 over 36 or 1/6. I couldn't help myself there. Now how about letter C? What's the difference between B and C? Do you notice the inequality? In letter C it says less than 4. In letter B it said less than or equal to. So in letter C, we are not allowed to have a sum of 4. It has to only be a sum of 3 or a sum of 2. And that's going to be 3 over 36. 236 plus 136. Okay. 2 more here, same distribution. We want the probability that the sum x is greater than 10, not equal to 10, but greater than. So that means a sum of 11 and a sum of 12. So that means you're going to add 236 plus 136 and get 336 or 1/12. Now how about greater than or equal to 8? Well, that means 8 or 9 or 10 or 11 or 12. Okay, how many is that? Let's see, that's 9, 10, 11, 12, 13, 14, 15, 36. So you see there's lots of variation with these. Let's do another one. How about this one? How about probability that the sum is 1? Okay, do we have a sum of 1 on here? I don't see that as an outcome, so that probability should be 0. How about this one? How about the probability that x is greater than or equal to 2? Okay, so that means a sum of what? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means the whole distribution, 36 over 36, or 1, right? So what's the probability we get a sum of 2 or more? Well, that's easy, it's 1, okay? How about this one? How about the probability that x is greater than or equal to 12? Okay, well, how many outcomes do we have that are greater than or equal to 12? Well, the answer is 1. It's only 12, so that should be 1 over 36. And how about this one? Probability that x is greater than 12. Do we have any outcomes here that are strictly greater than 12? The answer is no, so that should be 0. So 4 extra problems to take a look at there. So it's not uncommon for us to have you build a probability distribution and then ask some follow-up questions related to it. Now here's one that's not related to the distribution that we just created, but is an old final exam problem that deals with random variables. So here we've defined x and y to be something different, right? So x is a value from die 1, and y is going to be a value from die 2. And so the outcome is defined, we say, as an ordered pair, right? Die 1 comma die 2. So put another way, it's x comma y. Okay? That's important to note. Now it says find the probability that y is equal to 2 times x. So what does that mean? That means that the value on die 2 is twice as much as die 1. So let's look again at that ordered pair. We had the ordered pair x comma y, correct? That's going to be transformed into x comma 2x. Now why did I do that? I did that because we know that y is equal to 2x. Now we have to remember that the outcomes on the die, right, are 1, 2, 3, 4, 5, and 6. So let's see if we can figure out what those ordered pairs would be. So if x was 1, what would die 2 have to be? Well, that's 1 times 2, or 2. Okay? If die 1 was 2, what then would die 2 have to be? Well, that's 2 times 2, which would be 4. How about if die 1 was 3? Okay, 3 times 2 is 6. Okay. How about if die 1 was 4? What would die 2 have to be? That would be 4 times 2, which is 8. But wait a minute, we got a problem. I can't have the value of the die be more than 6, so that's not going to work. So that means if x was 5 and 6, that wouldn't work either. So it looks like these are the only 3 outcomes, right, that we're going to have to deal with in this case. Okay, so that's 3. Now, how many ordered pairs are there? Well, you can use your fundamental counting principle, right? If you know that there are two die, each die has 6 outcomes on it, that's going to leave us with 36. So this is going to be 3 out of 36. Now the next one's a little similar. Okay, we again begin with the ordered pair x comma y, and you'll notice this time we substitute for x, right? X has to be 2 plus y. So now what I need to do is to pick some values for y. Okay, so if we let y be 1, easy to start, that's why it's always at the start of the list here for the outcomes. What is the x coordinate going to be? Well, that's going to be 2 plus 1, that's going to be 3. Okay, what happens if y is 2? What's the x going to be? That's 2 plus 2 is 4. Okay, how about if y is 3? That's going to be 3 plus 2, which is 5. Okay, how about when y is 4? Well, 4 plus 2 is 6. Okay, and how about when, I'm running out of space here, y is 5? 5 plus 2 is 7. But wait, what do you know? We can't have 7, 5, right? 7 itself is not an outcome on the 6-sided die. Okay, so how many outcomes did we have? We had 4. So 4 outcomes out of the 36. So a little tricky there, and that's how we handle this particular set of problems. Okay, now we're ready for the big part, which is what the expected value is. Okay, so let's understand this. So the expected value for a discrete random variable x is equal to the mean of the probability distribution. So what does that mean? This means it's an average. Okay, and we actually call it an average outcome. That's the cool part here. So it's the average outcome. And more precisely, I hope you all are sitting down, it's a weighted average. And I know we talked about that in chapter 3. So what are the weights? The weights are actually the probabilities. Okay, that's the cool part here. So the weights are the probabilities. So look at the formula. So the formula, we use this capital E of x. Sometimes, usually the notation that I'll use is these hard brackets with x inside of it. Some textbooks use that. And look at the variable here, mu, okay, indicating that it's an average. Okay, so that's why that stuff is coming back to us. So what this is saying is we add up, there's the sum, the xi is the outcome, right? And look at this, this is the probability. So you are adding up the outcomes times their probabilities. That's what this formula is actually saying. Now let me clean this stuff up down here for a second. Because we've got another expression for this, another way of writing it. Sometimes textbooks will do this sort of thing. They'll say mu is equal to expected value of x. And what they'll say is it's x1 times p1 plus x2 times p2. And you keep doing this for all of the outcomes, okay? And so the xi here are the outcomes, and the pi are the probabilities. And of course, we'll do an example so you can see how this works. Okay, but whatever formula is useful. This is the more compact version of what I just wrote. Okay, so let's put this to use. All right, let me see if I gave myself some space. I did. Okay, we've got this story problem here, everybody's favorite. So it says, suppose Randall and Blake decide to make a friendly wager on the football game that they're watching one afternoon. So it says, for every kick the kicker makes, Blake has to pay Randall $30. For every kick the kicker misses, Randall has to pay Blake $40. Prior to the game, the kicker has made 18 of his past 23 kicks this season. Okay, so letter A says, what is the expected value of Randall's bet? Well, we got a little problem, guys. I can't figure this out because I need a probability distribution. Okay, so we got to build one. Okay, so we got to remind ourselves, what does a probability distribution show us? Well, remember, it shows us the outcomes, right? And it shows us the probabilities. Okay, now in this case, we have 2 outcomes. Okay, the first outcome we have is if the kicker makes it. And the other one is if the kicker misses. Okay. Now, something happens, doesn't it, when the kicker makes it? Okay, and the other thing we have to remember is this is from the respect of Randall. Okay, so that's important. So what happens when the kicker makes it? Well, I got to read the problem again. It says, for every kick the kicker makes, Blake has to pay Randall $30. So that means Randall is getting $30. Okay. Now, what happens when the kicker misses it? Well, it says when the kicker misses, Randall's got to pay Blake. So that's a loss for Randall, isn't it? So that's a negative $40. Okay, so hopefully that makes sense. So from Randall's perspective, the kicker makes it, he gets $30. When the kicker misses, he has to pay out. And so that's why it is negative. All right, now we need probabilities. Well, what does it tell us? This is prior to the game, the kicker's made, so there's this probability, 18 of the 23. Okay. Now the question is, what's the probability that the kicker misses it? Okay, well, here's the cool thing. We know that the sum of these probabilities has to be 1, right? So there are only 2 outcomes here. So if I take 1 minus 18 over 23, that's going to give me the missing probability of 5 over 23. Nice and easy. Okay, so now we're ready to compute the expected value. So here we go. So what it says we do is we take the outcome, which is $30, and we multiply by $18 over 23, its probability. And then we take negative $40 times its probability of 5 over 23. Okay. Now notice a couple things. I'm using the dollar signs to remind me of the units. So you have to have units here. Remember, this is an average outcome. The outcome here is dollar amount. Okay, so it has to match. So take a second, pause the video, run the computation. Okay, 30 times 18 over 23 plus negative 40 times 5 over 23. And what you should get is $14.78. Okay, so what does this mean? This means that Randall is making money. Okay, so Randall is making money here. Now, the reason I know that is because this expected value is positive. Okay. Now, if it were negative, what that would mean is that Blake is the one that's making the money. Okay. Now, couple things. People get a little nervous when they see $14.78. They ask, how is that possible when the payouts here are clearly even, right? $30 and $40 respectively. And what I would say to you is you have to remember that this is indeed an average. Okay, so what's happening is that if this game is played many times, and Randall adds up his winnings and subtracts his losses, on average, he expects to walk away with $14.78. We sometimes call this a long run average. Okay, a long run average. Now, there's another little fact here that we have to make sure that we're aware of, and that this game is not fair. So this is not a fair game. Okay. And in fact, Blake is an idiot for playing this game. Okay, because it very clearly favors Randall. And it was not obvious to see from the probability distribution. You actually needed the expected value to understand that. Now, can you think for a second, what do you think that the expected value would have to be in order to be considered a fair game? Hopefully you said that the expected value has to be 0. That's an important thing to make sure you have written down. So in order for the game to be fair, we need the expected value to be 0. It doesn't favor anybody. Now, if we had written this this distribution in the frame of Blake, okay, from Blake's perspective, then what we would have noticed is for Blake, the expected outcome would have been negative 1478. And what that would have told us is it's not in favor of him. Okay, so once again, from Blake's perspective, it would be negative 1478. For Randall, it's the positive. So that's really the cool part to this. And this is what casinos do, guys. They've got games that have far more complex probability distributions, but the expected values on those machines, those average outcomes, are always negative for us. And so what happens is the casinos, since there are so many people playing the games at any given time, they're making all sorts of money very, very easily. Now, in letter B, what they want to know is that the kicker attempts 4 kicks during the game. How much should Randall expect to win in total? Well, that's easy, because what you do is you take the $14.78, which is the average, right, we expect on a kick, average outcome here, and we multiply by 4, and what you end up getting is $59.12. Okay, and again, that's on average. Okay, it's on average. One more to go, and it's Peyton, who's trying to decide between 2 different investment opportunities. Okay, and so we've got 2 plans that are here. So let me just scroll down here. Which plan should he choose? So you've got plan A and you've got plan B. Okay, it's not obvious from what we have written here, and so what you have to do is you have to compute the expected values, okay, for each of the plans. And so what I would encourage you to do is to take a second, pause the video, and actually run the computation. So what you're going to do is you're going to take 1200, take 1200, and you're going to multiply by 0.1, and then you're going to add that to 950 times 0.2, and you're going to add that to 130 times 0.4, etc., etc. And you're going to get a number, and then you're going to do the same thing for plan B. Okay, so go ahead and pause the video and take a look. Okay, hopefully you have done that. Plan A, you should have got $24.50, and Plan B should have been $322. Now, many people look at this and they think Plan A is better because there's less negative outcomes, okay? But in fact, if you're wondering, well, why is there a sudden shift, right? You got to look at the probabilities of the outcomes that are positive, right? What those probabilities are, but also the amounts, the dollar amounts. That has a lot to play into this, and so sometimes there's lots of variation, and so it's not obvious just by looking at the distribution. You got to actually compute the expected value, and so Plan B in this case is certainly better. Now, what follows is some discussion about something called the law of large numbers. And what this deals with is a pretty interesting phenomenon. And it deals with the expected value, but something I called a long-run average. And so according to the law of large numbers, if a random phenomenon with numerical outcomes is repeated many times independently, the mean of the actually observed outcomes approaches the expected value. And so that's the idea behind law of large numbers. And so people often ask how large is a large number. And so what we expect is many, many trials. And so what that says is if you listen to how I said it with Blake and Randall's example, if they play that game many, 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 many times, Randall could expect to walk away with $14.78 on average. But they have to do it a lot, many, many trials, infinitely many. I don't think they have enough money to play that game that many times, but that certainly is the way to go. And this asks here this question: is there a winning system? This is how the casinos are doing it. Okay, and they often try to look for different ways to cheat the system, if you will, count cards, that kind of thing. But it certainly is very difficult to do. So some very interesting stuff here for you to read on your own. But in any event, that concludes Chapter 5, Section 5.1. So I hope you found it as interesting as I enjoyed presenting it to you.